In this video, we're going to extend some of the ideas that we saw in Chapter 7. Chapter 7, we're looking at properties of atoms. We considered things such as their size, both whether they were neutral atoms or ions, what were the energetics when we were removing electrons, when we were adding electrons. Now in Chapter 8, we're going to consider how the different atoms and ions could be bonded together. So in this video, we're going to look at aspects of ionic bonding. We've already been doing some things with ionic compounds. If I were to ask you to put together magnesium and oxygen and describe an ionic compound, if I asked what is the formula for magnesium oxide, I'm sure that would be an easy task for you. You would say that magnesium's in the +2 column, oxygen's in the -2, and this would be the resulting empirical formula. Let's try to connect this with different ideas that we've seen in Chapter 7. So if we're making ions, we're interested in the ionization energy and the electron affinity. These were properties of single atoms. Ionization energy when we're removing electrons, electron affinity when we're adding them. So let's first look at ionization energy. If I'm considering magnesium oxide, I could remove the first electron, so that's the ionization energy corresponding to removing one electron. I list the information of what's really taking place. Ionization energy is defined with a gaseous atom. I see magnesium is number 12 on the periodic table, so there's 12 protons. This would be the electron configuration. I would say that the effective nuclear charge acting on that outermost electron is +2. To remove the second electron, it becomes more endothermic. The shielding looks very similar, but I've removed some electron-electron repulsion, and I think magnesium plus is smaller than the neutral atom. If I were to go on and ask about the energetics to remove a third electron, I could, but this would be very endothermic. Look at the huge difference that I have in the effective nuclear charge as I'm now removing an electron from n=2 instead of n=3. So I can begin to wrap my head around why it's energetically very unfavorable to produce magnesium 3+. What about the anion? It's exothermic to add one electron to oxygen. Why would I rationalize that? Well, I'm adding the electron to an orbital that has a large Z effective. I can see why that would be exothermic, but trying to add a second electron, adding a negative charge to something that's already negative, that's going to be very unfavorable. And yet I know that the ionic compound is magnesium +2, oxygen 2-. This was an endothermic process, and this right here was unfavorable as well. So we need to figure out more in this chapter, how does that take place? How does ionic bonding actually take place, and how can we understand it energetically? So the big idea in this section, 8.2, is that the energetics leading to the formation of ionic compounds is going to include forming the cations, forming the anions, and then the manner in which these ions come together to form the ionic compound. We have three different learning objectives. We want to be able to define the concept of lattice energy, arrange compounds in order based on their lattice energy, considering charges and their sizes, and then be able to identify and write the Born-Haber cycle for any ionic compound, and use provided data to calculate the lattice energy. This final objective, that's what I'm going to talk about in this video. You might have seen notation like this where we're describing the electron being transferred from the neutral sodium atom to the chlorine to make a cation and an anion. So we have the transfer of the electron to produce the cations and the anions. This image is showing, though, that we don't end up with molecules. Recall when we have our ionic compound, it's this whole collection of cations, anions. We don't have a discrete molecule. We have this extended lattice that's being described by the empirical formula. So in this video, we're going to look more at the energetics of that extended lattice. So let's look at this in terms of sodium chloride. So first of all, think back to chapter 5. The standard enthalpy of formation for sodium chloride. Sodium chloride I'm showing as the product. What are the reactants going to be? How would we write this? Think back to chapter 5, how we considered a standard enthalpy of formation reaction. Recall within that we were making 1 mole of product and it was the reactants in their standard state. So I would use sodium solid to get sodium and 1/2 of CO2 to get my chlorine. This is showing pictorially what would happen. You could combine sodium and chlorine gas. We have the transfer of electrons taking place. And it turns out this is very exothermic overall as sodium chloride forms. So the value for that, it would have a negative sign. This standard enthalpy of formation for making sodium chloride, the ionic compound, very exothermic. As the image says here, it's highly exothermic as we have the coming together of the sodium ions and the chloride ions. So this is describing starting with the elemental form for the sodium and the chlorine and seeing what does it mean to have the ions now combined to form the ionic compound. Let's consider the energetics more closely here. So I list here at the top the standard enthalpy of formation reaction and some other reactions that we're going to consider along the way. So first of all, practice once again the standard enthalpy of formation reaction. What would it be if we're making sodium gas? What would it mean if we're making chlorine gaseous atoms? Same plan. Once again, we're making 1 mole of the product and we're starting with the element in the standard state. So these would be standard enthalpy of formation reactions if I wanted to get gaseous sodium, gaseous chlorine. So I have different steps here that are in the process. The process that we're going to see to go from sodium metal and chlorine gas to form sodium chloride solid. I bet you can predict several of these, whether they're exothermic or endothermic. There might be ones you're not sure on. So take a second, pause the video, reflect on that. You can either tell me which ones you know, tell me which ones you're unsure about. Share some ideas on this because I think it will help you in the next part. Look at what's going on. Do you think a particular step is exothermic, endothermic? Need more information? Unsure? Try to communicate your ideas. Let me share my thoughts on it. So this particular step, if I'm going from a solid to a gas, I know that's going to be endothermic. It takes energy to go from a solid to a gas. Now, that's a phase change. And now notice what we'd written earlier. That could also be considered the standard enthalpy of formation for sodium gas. That next step, that's the definition for the ionization energy. Remember, ionization energy is starting with the gaseous atom and removing an electron. I know that's always endothermic. The next one, I'm breaking a bond in CO2. Notice how that could also be considered as the standard enthalpy of formation to get Cl atoms in the gaseous form. I suppose it could even be written in terms of the bond enthalpy. That's another way of considering what does it mean to break the bond in CO2. But breaking a bond in CO2, bond breaking, always endothermic. The very last step, this one is the definition for electron affinity. And in this case, halogens, it's exothermic. So when I say that you have a good sense or might be able to predict these are all ideas that we've been seeing so far. They're all clustered together right here, but it's stuff that we've been working on. How did these all come together then? They're all being shown in this figure here. This is what's called the Born-Haber cycle. This is describing the energetics that you can use to describe the formation of an ionic compound. It looks a lot of information right at the start, but I know that you're going to be able to handle this. The goal within this, the objective, we want you to be able to identify and write the Born-Haber cycle for any ionic compound and use the provided data to calculate the lattice energy. I'm going to work through 2 examples to show you what I'm talking about. So let's try to make sense of the different steps. What I see in all of these, at the very bottom, the lowest in energy is the ionic compound. The first step up from that is the same description that I see here for the standard enthalpy of formation. It's saying you could start with sodium solid and 1/2 CO2 gas. That's the enthalpy of formation to form NaCl solid. It's exothermic, that's why the arrow is going down. What if I were to try to figure this out by recognizing that enthalpy is a state function? What would this mean to be able to figure out the steps by working around and seeing the other values? What are the other steps along the way? This one right here, that's the standard enthalpy of formation for sodium gas. It's saying if you start with sodium solid and 1/2 CO2 gas, take the sodium solid and turn it into a gas. Endothermic process. The next endothermic process is breaking that bond in CO2. So instead of having CO2 molecules, you have Cl atoms. That was considered in terms of the standard enthalpy of formation for the Cl gas. We have this step right here. If we just inspect on the different steps what's taking place, it looks like we're going from sodium gas to sodium plus gas plus an electron. That's the ionization energy. What do we go from this plateau down to the next one? I see a Cl atom, I see a Cl minus. So what we've done is we've taken that electron and we've added it to the chlorine to make the chloride anion. That's the electron affinity. So I had us initially look at these and make predictions whether they're endothermic or exothermic. So we would have a better sense when we're looking at this, are we looking at arrows that were going up or arrows that were coming down? If they're pointed downward, those are exothermic ones. Now, if we were to stop right now in the process, if we've made sodium ions, chloride ions, we are at a much higher potential energy than where we started. The key step that we have within this is this very last one. That's referring to the lattice energy. That's all of the different ions that we have as we think about their energetics as we are having them come together to form an ionic compound. All of those pluses, minuses coming together in this extended array. Looks like that's really energetic. Now, the actual definition for that is to say start with the solid, the ionic compound, and tell me the energy involved in taking 1 mole of it and separating it into all of the ions. That would be extremely endothermic. But we're interested then conceptually here thinking about the opposite of that. What does it mean to have all the ions come together? Wow, that's going to be really exothermic, and that is a key thing to understand why ionic compounds form. It is not the transfer of the electrons, because if it was only the transfer of the electrons, we would have been at a much higher energy level than we started. The key thing that makes them exothermic is this formation of a lattice as they all come together. Let's look at another example. I mentioned we can write the Born-Haber cycle for any ionic compound. So let's say we're trying to make it for this copper oxide. So at the bottom would be the ionic compound. The step above that would be the standard enthalpy of formation reaction. What would be the process that I would have along the way? I've got multiple steps here. Let's see if we can make sense of the steps. So we can look at each of the plateau to decide and help identify what's going on. So we're taking the copper solid and making it copper gas, endothermic step. We're breaking the bond in the O2 molecule, so we'll have oxygen atoms, endothermic step. We have an ionization energy to make it copper plus 1, another ionization energy to make it copper plus 2. Now let's begin to take the electrons and add them onto the oxygen. It's exothermic to add the first one, but I said it's unfavorable always to add a negative onto a negative, and that's shown pictorially here how we have another endothermic step. This is the point at which we've made our ions. We've made the copper ions, we've made the oxygen anions, the oxide. This is really a lot of energy compared to where we started. What's the key thing that then explains it? The formation of the lattice as those all come together. In this case, since we have all of the numbers here, we could calculate that lattice energy. We have all of the values here, and because it's a state function, we can combine them, and all we have is this missing step right here. Let me show you the values here. So the way that I do this is I'm going to start right at the bottom, and I'm going to look at the magnitude of these. And I see that I have a value, if I were to go up, of 155, 339, 249, 745, 1960. If I add all of those together, that would be the energy it would take to get to this plateau. Some of it comes back in this exothermic step, minus 141, and then I have to add once again because I have another endothermic step. Putting all of this together, that would be the energy that it takes to go from the bottom all the way to the top. So if I want to then say, what is this missing step? It would be another way that I could say, what is the energy difference between way at the bottom and way at the top? Or I had that backwards, way at the top, way at the bottom. So this would be then the way that you could use provided data within the Born-Haber cycle to calculate a missing segment within that, such as the lattice energy. So within this video, we've been looking at ionic bonding. We've looked just a little bit at the concept of lattice energy and saw how it was included in the Born-Haber cycle. I tried to generalize to show how the Born-Haber cycle applied for two different ionic compounds. Our objective on this is we want to be able to identify or write the Born-Haber cycle for any ionic compound and be able to use the data that's provided to calculate a missing segment like the lattice energy.